give, if they are chemical shift equivalent, they give only one signal, or whether they're not chemical shift equivalent, in which case they would split one another. And I drew up a few examples in which I showed you that if you have enantiotropic hydrogens, they do not split one another. If you have stereotropic hydrogens, they do split one another. What I want to do now is to give you a few more examples of that, but of a different type of structure. For example, if you have this structure and you want to decide whether these two hydrogens are chemical shift equivalent or not, what you do is in your imagination you replace each of them by some group. So let's do that. If you replace the top one by some group X, you'll get that. And if you replace the bottom one by the same group X, you will get that. Now it's quite obvious to you that these two structures are different compounds, and these two, in fact, are diastereoisomers. So these protons are diastereotropic, and consequently, you have in this compound 3 non-equivalent hydrogens, because these two are diastereotropic. This one is clearly different from that. Now, what you should do as a homework is problem 9.5, and it's 9.5 in the 9th edition as well, and you should also do 9.6, which is almost the same as 9.6 in the 9th edition. Now, if you have geminal hydrogens, those hydrogens can couple with one another, they can split one another if they're diastereotropic, but only if they are diastereotropic. So let's just look at an example to explain that. All of these hydrogens are chemical shift equivalent, and therefore they have the same chemical shift. They do not split one another. Therefore you get just one line. If you have this compound, then you will get 2 lines, and they are singles. So let me just explain to you why you get 2 signals and why each one is a singlet. Well, clearly the CH2 that's sandwiched between a nitrile and an oxygen is different. Those CHs are different from the CHs of the methyl, which is just an oxygen. And you know that if you have different electronegative groups on a carbon, sucking electron density away, chemical shift of the hydrogens on that carbon change. And you also know if you have a hydrogen on a carbon that's adjacent to a double or triple bond, then you also can get shielding or de-shielding depending on the relative orientation of the hydrogen and multiple bonds. So there's no problem, there should be no problem in your mind in realizing that you get a signal due to the methyl and a signal due to this CH2. But what's not so obvious is, should those signals be multiplets or should they be singlets? Well, let's first deal with this one. If I write it if I write it like that, let me label these hydrogens as A and B. If I want to find out if those hydrogens are chemical shift equivalent, I use the test that I illustrated here. I replace, say, hydrogen A by some group X, and then in another picture I replace hydrogen B by the same group X, and I ask myself, the two structures that I've got, what's their relationship? Well, if you do that, you'll find that the relationship is that the two structures are enantiomers. And so those hydrogens are enantiotopic. And enantiotopic hydrogens, or homotopic hydrogens, do not split one another. So you get for this signal only a singlet. These two hydrogens don't split one another. Now, what about these hydrogens? Well, if you replace each of the three hydrogens in three different pictures by some group X, you'll find you get the identical compound because there's free rotation about all the single bonds. And so all those hydrogens are chemical shift equivalent, so they don't split one another. But do these hydrogens split those, or do these split those? So let's answer that question. What I'm going to do is to draw the picture a little differently. One bond, two bond, three bond, four bond. And four bond differences between the hydrogens usually don't give splitting. And so for that reason, this compound consists just of two lines. And if you think about it, of course, the area under those two signals will be in the ratio 2 to 3, because the area under a signal is proportional to the number of hydrogens represented by that signal. Now I want to say something now about the splitting. You've seen a few spectra where there's a signal and it's split into 3 lines, and you've seen a few others where there's a signal and split into 4 lines. How do we work out that splitting? You know so far only that if you've got a signal for a hydrogen and it's next door to n equivalent hydrogens, then the signal is split into n plus 1 peaks. So if you've got one equivalent hydrogen next door, n plus 1 is 2, you get a doublet. If you've got 2 equivalent hydrogens next door, n plus 1 becomes 3. You get a triplet. If there are 3 hydrogens next door, n plus 1 is 4, you get a quartet. Let me show you a little bit more about that splitting. And let me tell you why it happens in more detail than I told you so far. I've got a substance like this. Clearly the hydrogen on the left is different from the hydrogen on the right. They have different chemical shifts, they have different magnetic environments. So let's look at hydrogen that I'll call A, and also hydrogen that I'll call B. Now hydrogen A, so that's not very neat, is it? If by some magical process I could switch off the influence of all the hydrogens in that molecule on hydrogen A, I would get just a single line, a signal on hydrogen A. However, if I then, again by some magical process, allow the other hydrogen to behave normally, that hydrogen, which behaves like a very little magnet, can align itself in two different ways, either with the field of the applied field or against the applied field. If it aligns with the field, it increases the field experienced by that hydrogen. If it aligns itself against the field, it decreases the field experienced by that hydrogen. And so this hydrogen experiences two different magnetic fields. And therefore it gives a signal at two different frequencies of the applied radio frequency. And therefore this hydrogen will be split into a doublet. And this splitting is called the coupling constant. And it's measured in hertz, which is just another name for cycles per second. Likewise, B experiences two different magnetic fields because of the possible orientations of A, and so B also gives a doublet. And the coupling constant between A and B, that's this coupling constant for signal A, they're the same. So if the distance between the two peaks for signal A is, say, 5 hertz, the distance between the two peaks for signal B will also be 5 hertz. So if you see a signal with a certain coupling constant, and then another signal with the same coupling constant, they may be hydrogens coupled to one another. Now, what about the situation for observing a hydrogen which is next door to carbon carrying two hydrogens? You all know, because I've told you several times, that in such a case, the hydrogen you're observing will be a triplet. So there are a couple of questions you need to know. And that is, why is it a triplet? And if it's a triplet, what's the relative height of the lines, of the three lines? You see, if there's a doublet, the relative heights of the two lines are the same. What about if there's a triplet? So let's have a look at the case of a hydrogen This is the hydrogen we're going to look at. I won't write the other substituents. We will just assume that the substituents are such that these two are homotopic or enantiotopic. So these two are chemical shift equivalent. Now what's the story? Well, let's again do this magical process in which we, by some means, we switch off or neutralize all the other magnets in the molecule except that hydrogen. It gives a signal whose position depends upon what electronegative constituents and double and triple bonds are attached. Now, by some magical process, we will allow one of these hydrogens to behave normally. What that hydrogen can do is to align itself with the field or against the field. And if it does that, this signal will be split into a doublet, because it produces, with the other hydrogen aligns itself with the field, it produces an augmented field. When it aligns itself against the field, it produces a reduced field. So this hydrogen here experiences now two fields. Now, by some magical process, we allow the other hydrogen to behave normally. It likewise will produce two possible fields experienced by this hydrogen. So each of these lines will be split again. And this distance here is the same, this distance is the same as that distance. Now what about the intensities of the line? Now the way to think about that is you've got two hydrogens next door to the hydrogen that you're looking at. How many different fields can those two hydrogens produce? Well, here are the possibilities. Both of these next door hydrogens can align themselves with the field. And they can do that in two ways, well, they can align themselves with the field, or they can align themselves against the field. Or one of them can align itself with the field and the other one against the field. Or the first one can align itself against the field and the second one with the field. So you can have that, or you can have that. So here, they're both with the field. Here, they're both against the field. And here, the first one is with the field, the second one against the field. And here, the first one is against the field, and the second one is with the field. So there are two ways of generating this total magnetic field. There's one way of generating that total magnetic field. There's only one way of generating that total magnetic field. Hence the ratio of the lines it is 1 to 2 to 1. Now what happens if you have next door to the hydrogen that you're interested in not two hydrogens, but three hydrogens? Now you know by the n+1 rule that in that case you get 4 lines. And the question is, how do you get those 4 lines by this analysis? And also, what is the relative intensity of those 4 lines? Well, you'll find out in a moment that relative intensity is 1 to 3 to 3 to 1. And the reason is that by having 3 hydrogens, there are 4 different magnetic fields that the observed hydrogen can experience. And those 4 different magnetic fields arise by the various combinations of orientations of the 3 hydrogens, the items that are magnets. One of those orientations is only one way of combining them. They can all be with the field. Another one, again, there's only one way of combining them. They can be all against the field. Or 2 of them can be with the field and one against. Or you can combine those, as I'll show in a moment, in 2 other ways, so that there are 3 ways of doing it. Now let me just make that clear in a moment, which I'll do now. Let's just, I suppose I better clean the wall and do it on the centre here. When you have only one next door hydrogen, it experiences only 2 fields, because there are 2 ways that the adjacent hydrogen magnet can orient itself. If you have 2 next door hydrogens, you get 3 signals, because there are actually 3 ways in which 2 hydrogen magnets can orient themselves. And of those 3 ways, one of them, there's only one method of doing it, both with the field, the other one both against the field, but there are 2 ways in which one of the magnets is against and the other with. Hence, the central line is twice as intense. Now, if we have a hydrogen that's next door to 3 other hydrogens, well, it's first split by one of them, then it's split by the second one, and then just doing it. It's split by the third one. Split by one of them, then each of these 2 signals is split by the second of the 3 hydrogens, and then each of these 3 signals is split by the third of the 3 hydrogens. So the question is, what's the intensity? Well, all of the 3 adjacent hydrogens can be with the field, or all of them can be against the field. Or you can have 2 with the field and 1 against. Okay, 2 are with the field, can be the top 2 with the field, 1 against, or it can be the top one and the bottom one with the field and the middle one against, or it can be the bottom 2 with the field and the top one against. So those are the 3 combinations. And likewise, you can have that combination, or that one, so you can see there are 3 ways of generating a magnetic field represented by this line, 3 ways of doing it for that line, 1 way for that, and 1 way for that. Consequently, the ratio of the of the 3 signals will be 1 to 3 to 3 to 1. And you probably guess that these ratios correspond to Pascal's triangle, which is that set of numbers, and you can continue. So that, very briefly, is how you account for the splitting. A particular hydrogen experiences modifications of the applied field produced by the possible orientations of the adjacent little magnets. And those little magnets, at least for hydrogen, each one can always be aligned with the applied field or against the applied field. And all this business corresponds to this N+1 rule. Now, so far, I've said hydrogens on the next door carbon. And the hydrogens have always been on the same carbons. You've got the CH, then a carbon, and then say 2 hydrogens on the next door carbon. But since these lines, these little peaks, are due to the orientations of adjacent hydrogens, you'll get the same effect if the adjacent hydrogens are not on the same carbon. One can be on one side, one can be on the other side. So let's have a look and see what happens in that situation. I have drawn up a spectrum of a compound. It's got lots of chlorines in it. And you can see that the spectrum shows three signals. At high field, there's the TMS signal, so that's not part of the compound, that's just the reference signal. And then in the middle of the spectrum is a triplet corresponding to one hydrogen, and at lower field is a doublet corresponding to two hydrogens. Well, having told you that, look, you don't have to be an Einstein to guess that the two hydrogen doublet represents these two, and the triplet represents this. That, you know, that's just guessing. Let me explain it to you. First of all, the two signals come at different chemical shifts. That's reasonable because the central hydrogen is on carbon carrying one chlorine, and the end hydrogens are on carbon carrying two chlorines, and so the end hydrogens are on carbon that's had a load of electron density sucked away from it. Therefore, the density of electrons around that terminal hydrogen is lower. Therefore, the opposing induced field by the circulating electron densities is also smaller. Therefore, the nucleus is not shielded so much from the applied magnetic field. Therefore, the applied magnetic field can be lower. Therefore, it occurs at the downfield. By a similar argument, the central one, this hydrogen, is surrounded by higher electron density, and so it occurs at higher field. But why do these two give only one signal? The reason is that those two hydrogens are chemical shift equivalent. You can easily put by symmetry. This is exactly the same as that. This one experiences two different magnetic fields because it's next door to two different little nuclear magnets. And those two nuclear magnets can be aligned with the field or against the field, or it doesn't experience two different, it experiences three different magnetic fields because of the adjacent nuclear magnets, one on the left, one on the right. Those two can be aligned with the field, they can be aligned against the field, one can be aligned with the field, the other against, or it can be the other way around. So you get a 1 to 2 to 1 triplet. So that's the explanation of this spectrum. If you have to interpret the spectrum without that knowledge, suppose you were just given the formula. Well, in a case like this, because the formula is very, very simple, it doesn't require much effort to write down all the possible structures, and then you could easily reconcile this one with that spectrum. But if you didn't want to do that, you'd say, look, I've got something that's next door to one hydrogen, and I've got something that's next door to two hydrogens, and you could use that information to quickly draw up that structure. Now, what you should all do is problem number 9.8. And it's 9.8 also in the ninth edition. Now what I'm going to do is to interpret for you so you know how to do it. You can get this in the lab today, I guess. How to interpret some simple spectra. Supposing you have a compound and it is C3H7I and its NMR spectrum one, two, three, four, five, six, seven, and 1, 2. That's at about 2 ppm, and this is about 4.3 ppm. That's the NMR spectrum of this thing, and the ratio is 6 to, that's rubbish. Ratio is 1 to 6. Now, when you see ratios of 1 to 6, one of the common things one would think of is maybe 1 hydrogen and 2 methyl groups. And as soon as you think of that, you realize that if there are 2 methyl groups, that means 6 hydrogens, and the n+1 rule would suggest that there's an adjacent hydrogen that's split by those 6 into 7 lines. You remember when I was drawing this, I counted 1, 2, 3, 4, 5, 6, 7. And so just by a cursory examination of this spectrum and the fact that the ratio is 1 to 6, you should, in your mind, write down a situation like that, and then, of course, since you know there's iodine there, you fill that in, and that, in fact, is the structure of the compound. Now, another way of doing this could be, you look at that structure, you know that it's got no double bond equivalents, so there are no rings, no double bonds, no triple bonds, so it has to be a straight chain. There are 3 carbons, so there's that possibility, and there's this possibility. And of those 2, on the basis of everything that you've had in the last few classes, it should be very easy for you to rule out one of them. Because this one has 3 different types of hydrogen. You get 3 signals, you only got 2 signals there. You have to be able to count up to 2. Not very difficult. And so even if you didn't understand most of what's been going on, you go for that structure. I want to do another one now. It's well, I don't know if it's a little more difficult, but at least it will illustrate for you what's going on. There are 4 lines here at about 5.8 ppm. That immediately tells you there's something either sucking electron density away quite strongly, or it's de-shielded by virtue of being next to an unsaturated unit. And then at about 2, there's a doublet, and the ratio of these things is 3 hydrogens to 1 hydrogen. Now the formula is that. There are several ways of approaching this. Depends how intellectual one wants to be. If one is very tired and doesn't want to display how clever one is, one would then look at the formula, realize that there are no double bond equivalents in that formula, and so there are not many possible structures. One of them is that, and the only other one is this. But the second one has chemical shift equivalent hydrogens, will give only 1 signal. This baby has 2 signals. Therefore, without thinking, you can write this down. If you wanted to be really intellectual, you look at this and say, it's a very high field signal. Corresponds to 3 hydrogen. Maybe it's a methyl group. In other words, a carbon carrying no electron withdrawing group directly. And then there's a low field signal that's split into a quartet. It must be perhaps next to a methyl group. But because it's a low signal, it contains a lot of electron-sucking groups on it. As soon as you work that out, you have to write down this structure. You don't have any choice. I'm going to do one more. So you've got a spectrum. It has two signals. Each is split into a multiplet. One of the signals is sort of medium down field, 3.7, not 37.3.7. The other one's at high field. So the 3.7 one is a triplet. That suggests to you that it represents a hydrogen on carbon next to three other hydrogens. No, sorry, next to two other hydrogens. The other one has 5 lines, which suggests that it represents hydrogen that's on carbon that is adjacent to 4 other hydrogens. So you've got hydrogen that's next to 4 H's, and you've got a hydrogen that's next to 2 H's. Now, how can you write a structure? It's not C8. What am I doing? It's C3. Okay. That's much better. You know, 3 is only a little bit different from an 8 because you just use 2. There's only 5 here. And how can you put these pieces together? Well, the way to put them together is like this, because these hydrogens amount to 4, and they are next to 2 homotopic hydrogens. These 2 hydrogens here are chemical shift equivalent by symmetry. This one is next to these 2 that are homotopic. That one is also next to it. So this is split into a triplet by that. And this one gives the same signal as that. But this one is surrounded on one side by 2 hydrogens. On the other side by 2 hydrogens. These 2 are chemical shift equivalent. And so this thing, by the n+1 rule, is split into 4 + 1, 5. So this is a downfield, split into a triplet. This is at high field because it's not directly attached to an electron withdrawing group. And it's surrounded by 5 possible orientations of little hydrogen magnets. So it gives a signal that's 5 lines. Now, as I told you earlier today, if this signal is coupled to that signal, and likewise this is coupled to that, the coupling constant here must be the same as the coupling constant there. So if the distance between this pair of lines is, say, 3 hertz, the distance between any pair of lines, adjacent pair of lines, is also 3 hertz. Now there's one other factor that you need to know about. If you've got a hydrogen on carbon, and next door a hydrogen on carbon, you know that the first hydrogen is split into a double. But there's another factor that's involved, and that factor is, what is the size of the coupling constant? Is it 1 hertz, 2 hertz, 3 hertz, 10 hertz, 8 hertz, 4.5 hertz? What is it? Now, the size of that coupling constant depends on a number of factors, but one factor is very, very important, and that is the angle, the dihedral angle between the two hydrogens. Let me show you what I mean by that. Here I've got a hydrogen on carbon, next to a carbon carrying a hydrogen. And I've drawn a Newman projection. And I've drawn it such that the hydrogen on the carbon nearest you is pointing straight down. The hydrogen on the carbon that's away from you is pointing straight up. And this angle is, in this case, 180 degrees, and that's called the dihedral angle. And over here, what I've done is I've taken the body, moved this a little bit. And now this is the dihedral angle, and it's clearly smaller. And if I moved it more, the dihedral angle would be 0. So the dihedral angle can be anything between 0 and 180 degrees. It turns out that the size of the coupling constant depends on the dihedral angle. And on page 411 of your book, they've actually got a graph. This is about 10 hertz. This one is 8 hertz. Then the dihedral angle here is about 90. And this is 0. And this is 180. So, you know from this picture that if you have two hydrogens with that relative orientation, dihedral angle of 90, or thereabouts, the coupling constant will be 0. If, on the other hand, you have a dihedral angle of 180, coupling constant will be quite big. And if you have a dihedral angle of 0, the coupling constant will be not quite as big. And if you have dihedral angles anywhere between, the size of the coupling constant will vary according to this curve. So, if you have a system that isn't freely rotating, if you look at these two hydrogens, their dihedral angle is 180 degrees. If you can't see that, just build a model. If you look at these two hydrogens, their dihedral angle is 60 degrees. And again, if you can't see that, and it is more difficult to see in that situation, in that picture, you just build a model. Now what you should do is problem number 9.11, which is equal to 9.10 in the ninth edition. Now, you probably think that this is terribly complicated. You ain't heard anything yet. But don't worry, because the additional complications are not within the scope of this course. Somebody's about to crack. Let me just mention to you the sort of complication that you can three different types of hydrogen. These two hydrogens will be coupled by the methyl group, and they will be coupled by the CH2. But these hydrogens are in a very different magnetic environment from these. And the coupling constant here is going to be different from the coupling constant over here. So if this is split like this with a certain coupling constant, each of those peaks will be split with a different coupling constant on this one. And so instead of this being split into n plus 1, 6, it will be more complicated. And it can get very, very complicated. And there are ways of dealing with that. But you need to be aware that that is a complication. And the other thing that you need to be aware of is that the spectra that I've dealt with so far are what are called first orbit spectra, and that means that the chemical shift difference the chemical shift difference divided by the coupling constant is B. So you've got a signal here, a signal there far away, maybe 200 hertz away, and the coupling constant is quite small. So that small number divided by 200 might be even 10. In a case like that, the spectra behave the way that I said. If the chemical shift difference between two signals divided by the coupling constant is smaller than 10, then all the stuff I told you is no rubbish. And the spectra are much, that's exaggeration, the spectra are much more complicated. But don't worry, you don't have to concern yourself with that.